Okay, so right now I want to talk with you about relations. And you may know this term when you learned about functions, because they say, is that a function or a relation, which is kind of a funny question. So 3, 17, 25, 39, and 43 are your suggested exercises. We're going to look at, of course, relations. We're going to look at graphs. We're going to look at X and Y intercepts. We're going to look at symmetries again, the same symmetries we saw in the previous section, but now for relations, for graphs, as opposed to just for points. So symmetries with respect to X and Y axis and the origin, like before. And I would like for you to work through examples 1 through 4 in the book. All right, so let's define relation. Even though you may have seen some other definition of relation, let me define relation for us here. So a relation, as far as this class is concerned, is a set of points in the plane. Now, you may have seen other definitions of relation. There are related definitions, no pun intended, but there are all sorts of things called relations. So this is just what we're dealing with in this class. I'm going to say a graph is a plot, which is a little redundant, a little bit circular, but it's a plot of the points of a relation. Okay? If a relation is defined by an equation, we sort of cut out the middleman and say we call the accompanying graph the graph of the equation. So rather than saying it's the graph of the relation determined by the equation, we just say graph of the equation. So let's do a quick example. Which of these points is on the graph of the given equation? Okay, so the points are going to be 2, 3, 1, 0, and 3, 2 root 6. And the equation is x cubed minus y squared equals 1. So solution. Now, while this definition would say that we're looking at if there's a point that's on a plot of a graph that is a relation, and I would have to, maybe if we weren't careful, we might think that I would have to sketch a graph of that equation before I could see whether these points are on it or not. But since the points are determined by the equation, we can just plug them in and see if they make the equation true. So we just plug in 2 cubed minus 3 squared. And what is that? What is 2 cubed minus 3 squared? That's 8 minus 9, and that is not equal to 1. So the first point is not on the graph. All right. Then we're going to plug in 1, 0. So we have 1 cubed minus 0 squared, and that equals 1. So that is, the second point is on the graph. Now what about 3 cubed minus 2 root 6 quantity squared? That might take a little bit of work. 3 cubed is 27. 2 root 6 squared, so we're going to have 4 times 6 is 24, which is 3, not equal to 1, so again, no. And that's it. Just to figure out which of these points is on the graph of the given equation, all we need to do is plug in those coordinates into this equation, and those that are on the graph of the equation will satisfy the equation, those that are off will not. That's it. All right, next, if a graph touches the x-axis, we call these points X-Intercepts. Same for Y-Intercepts. Okay, if they touch the y-axis, then we call them Y-intercepts. And probably you've heard this before, but I just want to make sure that we're on the same page here. So let's do an example. We're going to sketch a graph of y equals x minus 1 quantity squared and find its intercepts. All right, so to do this, emphasis on the word sketch. We're not going to worry about this being perfect. We're just going to maybe think about roughly what we know about this kind of thing. So, x minus 1 quantity squared minus 2. I forgot that. Okay, so what we want to do is find the x and y intercepts. So I'm going to start by finding the y-intercept. To find the y-intercept, that's where we touch the y-axis. That means we just set x equal to 0. So if we set x equal to 0, we get y equals 0 minus 1 quantity squared minus 2. This is 1 minus 2, which is negative 1. So the only y-intercept is going to be the point 0, negative 1. All right, so that's our y-intercept. Now let's do the x-intercepts. And that means we want to set y equal to 0. Okay, so we write 0 equals y, which is x minus 1 quantity squared minus 2. And we can FOIL out this this right-hand side, and we get x squared minus 2x plus 1 minus 2. Okay, so 0 equals, well, let's just simplify this. We get x squared minus 2x. So we got plus 1 minus 2. It's going to be minus 1. So now off the top of my head, I don't know if I can get if I can factor this by using just by unfoiling, because I'd need two numbers that multiply to be negative 1, which is all I can really think about is plus and minus 1, but then they need to add to negative 2. So that doesn't seem like it's going to happen. So let's try the quadratic formula, and let's just see what happens. Quadratic formula, we have that x equals negative b plus or minus the square root of b squared minus 4ac. And we divide this all by 2a. So let's plug in. So negative b is going to be positive 2 plus or minus the square root of negative 2 quantity squared minus 4 times negative 1. Times 1 times negative 1. Oh dear. 4 times 1 times negative 1. And we divide this by 2 times 1. Okay, so x equals 2 plus or minus what? Well, under here we've got 4 plus 4 divided by 2, and this is giving me 2 plus or minus the square root of 8 over 2, and this becomes, well, I can factor a 2 out of the radical, 2 plus or minus. If I factor a 2 out of the radical, that means that I'm writing this as the square root of 4 times the square root. Let me just go off to the side here and see what I'm talking about. If I've got square root of 8, I can write this as the square root of 4 times 2, which I can write as the square root of 4 times the square root of 2. And this ends up being 2 square root of 2. Right? So I'm going to factor out a 2, which means I pull a 4 out of the inside of that. So I've got 2 root 2 divided by 2. So I have finally x equals, I can cancel this 2, 1 plus or minus the square root of 2. And recall this happens when y equals 0. So we have x-intercepts at well, we've got 1 plus square root of 2, comma 0, and 1 minus the square root of 2, comma 0. So let's just do a real quick sketch. I've got a y-intercept at 0, comma negative 1. So 0, comma negative 1 is a y-intercept. And my x-intercepts are at 1 plus square root of 2. So 1 plus something a little bit more than 1. And at 1 minus square root of 2. So 1 minus something a little bit more than 1. And this tells me, so I've got those 3 points that I know are on the graph. And hopefully I've graphed enough quadratics to know that this is going to look like a parabola. So I've got a parabola that goes through these 3 points, and that tells me my parabola looks something like this. Okay, and that's a fine sketch. It doesn't have to be perfect. We'll do more on sketching graphs of equations as we go further, but I just wanted you to kind of see a basic sketch of a graph of an equation. Okay, so if some of this is a mystery to you, like if you're not familiar with parabolas or whatever, no big deal. This is just to say kind of what we're looking for. We'll do more on that later. So the last sort of set of topics I want to discuss here with this section is the symmetries. So we'll say that a graph is symmetric with respect to, you remember WR2, the x-axis. So I'm going to list several things here. The x-axis, so symmetric with respect to the x-axis if we get the same graph by swapping y with minus y. It's symmetric with respect to the y-axis if we get the same graph by swapping x with negative x. And finally, it's symmetric with respect to the origin if we get the same graph by swapping both. So what I want to do is just take a little bit of time and see some examples of these. So let's do an example of something that's symmetric with respect to the x-axis. So a graph that's symmetric with respect to the x-axis would be something that's maybe the same as it is as above, so below. Okay, so the same as it is up top as down below. Okay. Symmetric with respect to the y-axis is going to be a graph that is symmetric with the left and the right. So let's see something like maybe like that. So what am I saying here? On this one, I could flip this. If I could pull this out of the page and flip it upside down like this way, then I'd get the same graph. This one, if I could pull it out of the page and flip it left and right, you couldn't tell the difference. I mean, aside from the fact that my hand is a little squiggly here, that this is roughly a mirror image on the left side as it is on the right side. Now, symmetric with respect to the origin is going to be a rotational symmetry. So it's going to be like, well, that's a little bit rough. Let me get in a little closer here. Okay, so something like this, where in theory I could take this thing and if I rotate it all the way upside down, I should get roughly the same picture. Okay, so the idea is that it's symmetric with respect to me spinning it around 180 degrees, we'd say, or spinning it around halfway. And that is what I wanted to cover for section 1.2.